This is an AQA A-level chemistry topic and it's year 13 kinetics. So following on from year 12 kinetics, and this is part 3 where we're going to start to look a little bit more into rate equations and how we can use them mathematically. I'm going to recommend that you pause on the activities, try them for yourself and see what's going well and what might need a little bit more time and effort spent on it. So in here, we are going to look at how the order of a reaction can be found experimentally. We're going to look at how the change in concentration affects the rate constant and how a change in temperature affects the rate constant. And when practicing, in general, always have a go. There are so many past paper questions out there that allow you to really dig into some of the examples we're going to see later in this video. But to begin with, we're going to look at how we can show zero, first and second order reactions graphically. A reminder from the last video, if something is zero order, changing its concentration has no impact on rate. If something is first order, the change in concentration is directly proportional to the change in rate. And if we look at something that's second order, then whatever change we make to the concentration, we square that to show the impact it will have on rate. So what would that look like graphically? Well, I'm going to start by drawing out, and it is just sketching. I've got my zero, my first and my second order axes, and I'm going to spend the time just to really point out the importance of actually labelling those axes. And we could go further. We could put units on there, mol dm to the minus 3 for concentration, mol dm to the minus 3, s to the minus 1 for rate. Now, zero order, remember, changing concentration has no impact on rate. So it's really straightforward. It's a straight horizontal line. Whereas we're essentially saying that with a first order reaction, if doubling concentration doubles rate, trebling trebles, it's directly proportional. And that's represented by a straight line graph. But in second order, we are saying that if you double, it goes up by a factor of 4, treble goes up by a factor of 9, quadruple, rate goes up by a factor of 16. So the graph would actually look like this. You need to be familiar with the shapes of these to be able to recognize or sketch them. But we could take it a step further forward and we can look at second order. What could you plot relating to second order reactions that would give you a straight line? And I've got the graph here. We're going to put the axes on the labels, and we've still got rate on the y-axis. But if we want a straight line, we could say here that rate is directly proportional to the square of the concentration. So we'd be looking at concentration squared. Now, what we're going to do now is take a look at some examples of rate equation questions. And as I say, there's just a couple within this video. We're going to do 2 or 3, but there are many, many more out there, and practice is key on these to get confident with them. So let's start, have a go at this one. And we've got here some data, one experiment between A and B. It's been done 3 times, varying concentrations of A and B, and we then measure the rates. So what is the rate equation for this reaction? Well, the key to this is comparing runs or experiments where only one thing has changed. So if I look at experiments 2 and 3, where you can see that I have halved my concentration of A, I then want to look at what impact that has had on rate. And you can see that's gone from 8.64 by 10 to the minus 7 to 4.32 by 10 to the minus 7. It's halved. So that's directly proportional. And that tells me that this is first order with respect to A. Now let's see what we can do with B. Well, on experiments 1 and 2, I can see that I've doubled B, but I haven't changed A at all. So any change in the rate is entirely down to the change in B. And what we see here is when we double the concentration, the rate's actually gone up from 2.16 to 8.64 by 10 to the minus 7. It's quadrupled. So that shows us that this is second order with respect to B. And if I now know that, I can do my rate equation. Rate equals K, never changes. A, first order, I don't need to put the 1. B, second order, so the B as a power. So let's move on to a slightly more complicated one. On this one, I'm going to look at experiment A, where I'm going to look at A, sorry, by comparing experiments 1 and 3. And you can see here that I am doubling the concentration of A, but there is no change to the concentration of B or C. So any change is entirely due to the change in concentration of A. And we can see that I'm doubling A and I'm quadrupling the rate. So that tells me this is second order with respect to A. I'm going to go to C next. You don't need to do these in order. And if I look at C, I'm going to compare experiments 1 and 2, where I'm not changing A or B's concentration, but I'm doubling the concentration of C, and I can see that has no impact on rate. Now that tells me it's zero order, so C to the power of 0, which I won't include because you'll remember from the last video and from your wider reading and learning that anything to the power of 0 is equal to 1. So that leaves us with B. And for this I'm going to compare experiments 1 and 5. And here's where these questions can get a little bit more complicated. Because if I compare them, you can see that B and A have doubled. But I already know what impact A would have. A doubling would have quadrupled because we know it's second order, and that would have taken it to 28 by 10 to the minus 4. So actually, we know that by doubling B, we have taken it from 28 by 10 to the minus 4 to 56 by 10 to the minus 4. Doubling B has caused the rate to double. So that tells us this is first order with respect to B. So when I put all of that together into my rate equation, I get rate equals K A squared times B, and I don't include C because that was zero order. Going to take a slight sideways turn here, and we want to look at the effect of temperature on the rate constant K. You can see here that we know from Maxwell-Boltzmann that if I increase temperature, we have more particles with energy greater than or equal to the activation energy. Essentially, we know that increasing temperature increases rate. So using all of this information, how can we show how K is impacted on by a change in temperature? See what you can do. Now on here, what I'm going to start with is the rate equation. I've picked any random one. I've done Ka times B, but you could do this with any. If I rearrange that to make K the subject, you can see that K is rate over A times B. And what that essentially means is that in a given reaction, if the only thing we're changing is temperature, then increasing temperature will increase rate. And if rate is increasing but A and B are staying the same, then we can actually see that K is proportional to rate. So increasing temperature will always cause an increase in K, the rate constant. So let's move on and let's take a look at one final question in this video. And you can see here that you're using another one of our tables. Deduce the order with respect to P, then Q, then the overall order of reaction. Well, P, I'm going to start by comparing experiments 1 and 2, where I double P, but I keep Q the same, and I've actually quadrupled the initial rate. That tells us it's second order with respect to P. But with respect to Q, I'm going to compare experiments 2 and 3. I'm doubling it with no change to P, and there's no change to the initial rate, which means that it's zero order. The overall order, you simply add together the two orders, the orders of all reagents, and that tells us overall it is second order. To finish off, we have got a few more on that same experiment. So I've brought the data across once again, and I'm going to put the overall rate equation in because it's K times P squared, because we know it's second order with respect to P and zero order with respect to Q. So you're then asked to use the data for experiment 1 to calculate a value for the rate constant and state its units. Well, we've got all of the information in experiment 1 that if we rearrange to make K the subject, K is rate over P squared, concentration of P squared, we get the values directly from it, 0.002 over 0.5 squared. When we do that, it comes to 0.008. In terms of the units, we can substitute the units for rate and concentration in. I've done that over on the left-hand side here, and we can cancel out concentrations. Mol dm to the -3 and mol dm to the -3 gone. So putting it into standard form, I have mol to the -1, dm3, s to the -1. And to finish off, it's asking here about comparing experiment 1 to experiment 2 and experiment 2 to experiment 3 to show how the value of the rate constant would change, if at all, if the concentration of P and Q were increased in a series of experiments. Now, do bear in mind, this question comes up very commonly, but K is dependent on temperature only. So the answer will always be there is no change unless you're talking about temperature. But let's have a look at what we can see here. If I look at experiments 1 and 2, if I double A and I quadruple the rate, if I think about what's going to happen in the numbers here, then doubling the concentration is essentially concentration doubled squared, which is times 4. So that is counted. It's sort of countered by the rate going up by a factor of 4. K would be identical. In terms of the second one, experiment 2 and 3, the only thing that's changing is Q, and Q isn't actually even a part of the rate equation, so would have no impact. But the key message to take away here is remember that K is specific for a specific reaction at a specific temperature. Changing concentration will not change it. That takes us to the end of this video. Thank you for listening, and goodbye.